Move on to our last paper, Dear Lynn, with developing synthetic individual level population data sets.
My name is Julie. I'm from candidate from AutoCarto University. Today I'm here to share one of my research from my dissertation project, which focuses on developing synthetic individual level population data for map contextualization. So first, what is map contextualization? I want to start from two different viewpoints of map making. The first viewpoint is based on a very popular premise that we as cartographers are engaged in an objective or scientific form of knowledge creation, and maps are the carriers of those scientific or objective knowledge. And we sometimes just perceive maps as the facts, the representations of geographic facts. And there is another viewpoint of map making, which consider map as social constructions. So here, maps are perceived as artifacts, which are deeply situated in the political, social, and cultural context. And when we are interpreting those maps, we really need to first understand the context during which the map is made. And then we can better interpret those maps, better understand what the maps represent. I want to illustrate concepts of map contextualization using an example of census data and census maps here. The United States Census Bureau, which produces the census data, is founded by Title 13 of the US Code, which states that the Census Bureau cannot make any publications of the census data that will disclose individual identities and threaten individual privacy. And as a result, to comply with this privacy law, the Census Bureau have been taking a lot of actions and practices to protect individual privacy in census data. And in 2020 United States Census, the Census Bureau used a privacy protection technique called differential privacy, which adds statistical noise to the census data before it is published and mapping. So under this context of mandatory privacy protection, how can we better understand the maps with the privacy preserving census data? If you look at the US Census Bureau map gallery, there are lots of maps produced by the Census Bureau, and many of the maps have notes underneath these maps saying that there are some privacy protection techniques that have been applied to this data prior to mapping. But there's very little information about like how differential privacy and other privacy protection techniques may affect the census maps, and also how will they affect the way we understand and interpret the census maps. So a very important approach to help readers understand or interpret different maps is to ensure the transparency of map making, because transparency ensures or guarantees the reproducibilities, and map readers will have the access to actually reproduce the map making and understand how uncertainties may be involved in map making, and they will have a better understanding of how they can appropriately interpret the maps when they're reading the maps. And to ensure transparency, full transparency of the map making process, there are several key components. For example, the map readers may want to know like how the cartographers decide their map designs, and also how the different labels are placed on the maps, and also like what are the data selected, how are they selected, or how are they pre-processed before their maps, and maybe also how the data are sliced before mapping. And an important component here is the data that are selected for our mapping, because the data convey information that we want to communicate through our maps. However, there are many raw data that are mapped are not are sensitive and they're not made available to the public. For example, the individual level population data, like the census microdata, when these data are mapped, what we can have access to is really a map instead of the data. So that really harms the transparency of the map making process. And readers can all the readers have access to these maps. They can't actually reproduce the map making process, and they don't have a very good understanding of how uncertainties can be involved in the map making process. So there are two objectives of this research. The first objective is to develop a synthetic individual level data set that can be realistic and can be suitable for public use. And the second objective here is to illustrate how to use this synthetic individual level data set to help readers better understand the context of map making and understand how they can better interpret maps when they're reading a map. The methods we develop involves 3 steps. The first step is to collect publicly available census tables as our aggregate data. So every 10 years, the United States Census Bureau will collect individual level data from census respondents, and that's an enumeration of the US population. And there are many, many tables coming out of the census. And these tables provide population counts and other statistics of the demographic information in different geographic units in the United States. So we collect these data as the aggregate data that will be involved in our modeling process. And in the second step, we create matrix representations to illustrate the individual level data we want to synthesize. And the aggregate data we collected from the United States Census Bureau, and also the queries that are used to aggregate individual level data to aggregate data. So here I use an example to illustrate how to create these matrix representations. So here, suppose that we want to create an individual level data set with, for 2 blocks, and each individual in these 2 blocks have 2 attributes, sex and ethnicity. So the individual level data will have the rows representing different combinations of attribute values for these 2 attributes we selected. And each column will represent a geographic unit. And each element in this matrix here will be to be determined by our model, and they represent the population counts in the geographic unit that can be characterized by the attribute values in each row. And then we represent the aggregate data in a similar manner. So each row in this matrix will represent an attribute, and each column represents a geographic unit. And then finally, we design a query matrix to aggregate this individual level data to the aggregate data. For example, the first row of this query matrix is to aggregate individual level data to count number of females in each census block. After we create these matrix representations of individual level data, aggregate data, and the query matrix, we formulate an optimization problem to determine the value of each element in the individual level data matrix. And the objective here is to minimize the square difference between synthetic and the actual census tables. And we use a constraint to ensure that we have integer decision variables. We conduct a series of computational experiments to test the effectiveness of the proposed approach, as well as to illustrate how the synthetic individual level data can be used to contextualize census maps with privacy preserving data. And we select 11 census tables from the 2010 United States Census data to model or synthesize our individual level data set. And the census table we selected are for 2 counties in Ohio, the Franklin County and Guernsey County. Franklin County is a urban county, and Guernsey County is mostly rural. And these 2 counties represent different demographic compositions and population size across the United States. So that's the reason why we select these two counties as the study area. And we want to simulate for our computation. We want to simulate an individual level data set at the census block level, and each individuals are expected to have 5 attributes, and we list the attributes here. And accordingly, tables we selected contains the population counts broken down by 1 or more of these 5 attributes at the census block level. We conducted a series of technical validations to examine the effectiveness of the proposed approach. So first, we compare our synthetic individual level data with the original data from the Census Bureau. And because we select 11 census tables for our modeling process, we have 11 subplots here to examine the relationship between the synthetic and the actual census tables. If we just focus on the plots for table 5, P5, we'll be able to see that the data points are mostly lie in a straight line. And we also compute the correlation coefficients between these two sets of data, which is 1, and is the same for the rest of the subplots. And the results here suggest that our synthetic data can well represent census data. We also conduct external validations to examine the effectiveness of our approach. Here we compare our synthetic data with an external data set that's not involved in our modeling process, which is the American Community Survey Public Use Microdata Sample, ACM PUMS. And again, we map the relationship between ACM PUMS and the synthetic data we generated. And the result shows that our data can match pretty well with the ACS PUMS as well. So after we obtained the synthetic individual level population data and conducted the technical validations, we use these synthetic population data sets to sort of help users to contextualize or help them to better understand how to interpret census maps with privacy preserving census data. And the methods here involve 2 steps. For the first steps, we implement the differentially private algorithm used by the Census Bureau on our synthetic data set. And this algorithm involves 2 steps. So first, we inject the noise into the synthetic microdata. And then, so the noise are injected to microdata at different geographic levels. And then in the second steps, we process data at different geographic levels to ensure that they're consistent with each other. And so the second step of our process is that we map the original synthetic population data and the differential private population data, and to examine how differential privacy can affect maps with census data, and how can we better interpret maps with census data. So here we map the percent of Black or African Americans using the original synthetic microdata and the differentially private synthetic microdata. We also compute the percent error to indicate how differential privacy may affect census data and census maps. And there are several takeaway conclusions from these maps. So first, we can find out for most of the areas in our study regions, the percentage error, they're not 0, which means that the use of differential privacy can introduce a significant level of uncertainty in our mapping. And we can also notice that the level of uncertainty is not homogeneous in space. And from our mapping here, we're also able to identify which areas will have higher levels of uncertainties. For example, we'll find that areas with low percent of Black or African Americans will have higher values of percent error, and then higher levels of uncertainty. So that will help us to better understand, or help readers to better understand the maps creating with census data that are privacy preserved. So as a summary, in this study, we describe how to generate a synthetic individual level data that can be used or that can be used for the public and can be utilized to contextualize the map making process. And we also illustrate how the use of these public use synthetic data can be used to facilitate readers to understand the context of maps. And in the future, we would like to expand the scope of these data sets beyond the United States or to other regions. So, yeah, thank you for listening.
Good. Questions?
Yes, thank you for your presentation. I would like to raise two ethical concerns. So here, to my understanding, you can examine or infer the individual level data to de-aggregate the aggregated data to individual level data. The first point is, what if this data is used by others to produce some unethical outcomes? Because now we have the individual level data. So then it seems like it is a process of deprivate the data. So that's my first concern. And for the second one, it's about the algorithm itself. It seems that you didn't have the validation data because you don't have the individual level data. So how to validate that your algorithm it is effective?
Yeah, that's very good questions. So for the first questions, it is actually a reverse problem from the problem we described in this paper. So in this paper, our goal is to minimize the difference between our synthetic data and the actual data, right? So a reverse problem to consider is that if we have enough aggregate data, we may be able to completely reverse the actual individual level data collected by the census bureau. So a problem to consider here is that how can we publish as much as census tables while also maximize such error between the synthetic data we will be able to create and the actual census microdata. So that will be a research direction that can be extended from this research. And for the second question,
yes, how did you validate your algorithm was effective because you didn't have the individual level data?
Yeah, so we actually have external validation here. So if you look at the ACS PUMS data, it is a sample data from the census microdata, where so it is the sample of the real population. And we compare the distribution between our synthetic microdata and the ACS PUMS, and the distribution, as you can see in these two figures, the data points here are mostly on a straight line. And we also compute the cosine similarity between the ACS PUMS and the synthetic data we created. And numbers are shown here. So they're pretty close to one. So that's a way to validate our synthetic data. Yeah.
I actually have a question for you. So the areas that you mentioned where you had the larger percentage of error, you mentioned that your variable was a very low occurrence.
Mhm.
Those are also really rural areas. And I'm
Yeah.
wondering if it's more a connection of the low population density
Yeah.
and that you would find the same problem with other variables as well, just because there are low occurrence of all variables.
So if you look at the maps, okay, so we actually examined two counties. One is the Franklin County, which is an urban county and has a lot of population compared to Guernsey County, a rural county. And if you compare these two maps, you'll find that Guernsey County has a lot higher percentage error compared to the maps of Franklin County. So based on our results, we'll be able to find out potential privacy will affect areas with smaller population size and maybe less diverse more significantly. And yeah, that's like a finding for us to help us better understand the census maps, because sometimes when we look at the census map, we just assume that everything there are right, or they're of the same level of uncertainty, something like that, but that's not true all the time. If we look at, the maps, we will be able to reproduce. So, yeah.
Other questions? Okay, we have a few minutes left, so if there's any residual questions for our earlier presenters. Take those, or we can skip out and get to the snacks early. Thanks, everybody, for a great round of presentations.